Hey guys, today we are putting in use all that information that we learned last week about how to find asymptotes, both horizontal and vertical asymptotes, to actually put some stuff on a graph. So today we're talking about graphing rational functions in standard form. Now before we get to graphing, we need to talk about some specifics about our graph. First off, we have normal graphs called continuous graphs. Continuous graphs are just ones like linear, quadratics, things we've learned about before that just go straight through and don't have any breaks. Well, today, right, we're going to have asymptotes. And with asymptotes, we actually end up with what's called discontinuous graphs. So these asymptotes break up my graph into spaces where my graph cannot go. But there's also another type of discontinuous graph, and that is if we have a hole in our graph. So if there is a hole in our graph, sometimes that happens whenever we have an undefined value that doesn't actually create an asymptote. And let me explain why that works. So a asymptote is what's called non-removable discontinuity. It's discontinuity. And that is just like what we're used to thinking about whenever we drew our asymptotes on. But what if we could remove one of those asymptotes? Let me give you an example. What if we had this equation where we have y equals, what if we had this equation where it's y equals x plus 3 times x plus 2 over x plus 2? So as you can see, I have an undefined value for this x plus 2. If we took that x plus 2 off the side, set it equal to 0, we would have an undefined value at x equals negative 2. And so normally I would put an asymptote right there, vertical asymptote at x equals negative 2. However, what we're going to do instead is look at the top and we can see, oh, I can actually cancel that out. I can cancel that x plus 2 out with this x plus 2. And that leaves me with just y equals x plus 3. So x plus 3, that's what's graphed over here. But you'll notice there is still a hole here. And there's still a hole because even though I was able to cancel it out, it still counts as an undefined value. So I still have a hole at negative 2. Okay? Now, it isn't an asymptote anymore. It's just a hole. But we still have to remember that is one of my undefined values. So if we can factor the top and bottom and cancel something out, instead of making an asymptote all the time, it might make a hole that we can look for. Okay? All right, so let's turn the page and let's take a look at a couple of these problems. So first off, I have 2x squared over x squared minus 9. Now, our first step, we got to remember, is my graph going to be Bobo, Bottom, or is it going to be eats DC? So the first thing that we do is we're looking for our horizontal or our slant asymptotes. And we have to remember, is it bigger on bottom, bigger on top, or are the exponents the same? So for this one, we're going to say, okay, my degree on top is 2. My degree on bottom is 2. So degree on top is 2. Degree on bottom is 2. Okay, so that shows me that this one's going to be a eats DC problem. So we need to divide the coefficients. My coefficient for the first one is 2. My coefficient for the bottom one is 1. So my horizontal or slant asymptote, this one's going to be a horizontal asymptote. It is not going to be a slant asymptote. And my horizontal asymptote is going to be y equals 2. All right? So this one's an eats DC problem. And we were able to find my horizontal asymptote. Next, we're going to try to simplify this to see if there are anything that cancels out, anything that helps us find it. And then we're going to use that to find if I have holes or asymptotes or anything like that. So, first off, before I forget, let's go ahead and graph this first horizontal asymptote. So we're going to have a horizontal asymptote at y equals 2. That's my horizontal asymptote. Next, I'm going to simplify this. What I'm going to do is we are going to just factor the bottom. And see, can I factor the top? No. Can I factor the bottom? Yes. X squared minus 9 can definitely factor. It can factor to be x plus 3 times x minus 3. Okay, now, can't factor the top. We have factored the bottom. Is there anything that can cancel? Unfortunately, no. Nothing can cancel out. So, if nothing cancels, then we are going to have no holes in my graph. In other words, there's no holes because nothing cancels. Okay? And so we are just going to look to find my vertical asymptotes. Now remember your vertical asymptotes. Your vertical asymptotes are your undefined values that do not cancel. Vertical asymptotes are undefined values that do not cancel. So we're going to look here and here. So my undefined value for here and here, my undefined value for this one, this x plus 3, is going to be the opposite. So we're going to have an undefined value of x can't equal negative 3 and x can't equal positive 3. And that's going to tell me what my vertical asymptotes are. So we're going to have a vertical asymptote at x equals negative 3 and a vertical asymptote at x equals positive 3. Now, we can actually graph that on my graph right here. We can put one. We know they're not holes, so we're going to actually put it there. So we're going to have one at x equals negative 3 and one at 1, 2, 3, x equals positive 3. Now, I'm sure this looks really freaky. We have two vertical asymptotes on the same graph. Are you crazy, Mr. Martin? Well, maybe, but what we're really looking at is we're just going to be able to draw instead of just drawing in 2 sections, we're going to just draw in 3 sections. So we just have to figure out what those 3 sections are. The way we figure out what sections work is we find where my x and y intercepts are. If I had an x-intercept over here, I would draw in this section. If I had an x-intercept over here, I would draw in this section. If we have an x-intercept over here, we would draw in the middle section. So it helps us figure out where we put our stuff. So remember, to find our x-intercepts and our y-intercepts, we just make the other version 0. So what we're going to do is I'm going to take the factored section, because it's easier to work with a factored piece, and we're going to take that off to the side. And what we're going to do is we're going to plug in what we can to be able to find my missing 1. All right, so starting off, we are going to take my first one, find our x-intercept. So I'm going to go 0 for y equals 2x squared over, and you can write the factored out section or you can write out the original, but I'm just going to go x plus 3 times x minus 3. Okay, now we are looking for our we're looking for our x-intercept. So we're going to solve for one of my x's up here. To solve for my x, we need to clear out this fraction. So to clear out the fraction, we're going to multiply by what's in the denominator. So I'm going to multiply both sides by x plus 3, x minus 3. Multiply this side by x plus 3, x minus 3. Now here's the deal. This and this cancels. So cleared out that denominator, and all I'm left with is 2x squared here, and x plus 3 x minus 3 times 0 is still just 0. 0 times anything is still 0. So we have 0 equals 2x squared. Now, we are going to need to work to get that x by itself. So what I'm going to do is I'm going to divide this side by 2, divide this side by 2, and I'm going to get x squared equals 0. Then, to get that x by itself, we're going to square root both sides and get x equals 0. So my first one, my x-intercept is going to be at 0, 0. That easy. It's just going to be both those. So we're going to have an x-intercept at 0, 0. So I know that point's going on my graph. Next, my y-intercept. My y-intercept is going to tell me we need to plug in 0 to find my y-intercept. So we're going to take the same thing. We're going to go y equals 2 times 0 squared over 0 plus 3 times 0 minus 3. Okay, 0 squared is 0. 0 times 2 is 0. 0 plus 3 is 3. 0 minus 3 is negative 3. 3 times negative 3 is negative 9. 0 divided by negative 9 is 0. So I have a y-intercept as well at 0, 0. I don't even have to graph that one on there. Now that we know what it is, I want you to understand something. Whenever we draw a graph, we're going to go in like alternating sections. So since I know that I fill this section in the middle, I can go ahead and draw that. We can draw this section where we're going to hug this asymptote and hug this asymptote. But that also means that I'm probably going to have a section here in the top left and here in the top right. So we can draw this one there, this one there, this one like this one like this. Okay? I want to remind you that you can use Desmos.com to help you graph these out and see what these are supposed to look like. All right, continuing on, we're going to take a look at our domain and range. My domain is going to be all real numbers except whatever our vertical asymptotes or holes are. So my vertical asymptote is x equals negative 3, x equals positive 3. And so that's going to say that that's what x cannot equal. It can't equal negative 3 or positive 3. So we're going to go just like we've done in the past. Negative infinity to negative 3, union, negative 3 to 3, union, 3 to positive infinity. Okay. Now my range. My range is going to correspond with my horizontal or slant asymptotes. My range is we're going to have a horizontal asymptote at y equals 2. So we're going to go all real numbers except y can't equal 2. So we're going to go negative infinity to 2, union 2 to positive infinity. Okay? All right, so remember, first step, look at Bobo, Botner, ESDC. That gives you your horizontal asymptote. Second, simplify it to tell what your holes and vertical asymptotes are. Third, find your x and y intercept. Graph, and remember you can use Desmos.com to help you graph it. Fourth, write your domain and range. All right, that's all there is to it. Let's take a look at number 2 now. So number 2, once again, we're going to be doing the same thing. We have this one, and as we're looking at this one, we're first, is it Bobo, Botner, or ESDC? Well, my highest degree here. Okay. Goodness. All right. So my highest degree on top is 2. My degree on bottom is also 2. So that means this one is a ESDC again. So we got 2 in a row. That happens quite a bit. So then, leading coefficient here is 1 and 1. So my horizontal or slant asymptote is just y equals 1, because 1 divided by 1 is 1. So we can draw a horizontal asymptote at y equals 1. Just like that, super easy. We know that about my graph. Second, to be able to simplify this, you're going to factor. So I'm going to factor the top and the bottom. The top can factor to be x plus 5 times x minus 3. The bottom can factor to be x, let's see here, x minus 3 times x plus 2. Okay, so we were able to factor the top and the bottom. Remember, you get your x and plus to do that. I just did that kind of in my head. Negative 3 times 2 is negative 6. Add together, we get negative 1. 5 times negative 3 is negative 15. 5 plus negative 3 is 2. Okay, so listen. This tells me what my undefineds are. We're going to have x can't equal 3 and x can't equal negative 2. Now we just have to decide, are these holes or are they vertical asymptotes? So we look back, and can any of these cancel? Yes. This x minus 3 and this x minus 3 cancel. So that means we're going to have a hole where wherever x equals 3x. That's a hole, not an asymptote. But I am going to have an asymptote at x equals -2, because that's going to actually be a real, that doesn't cancel. It's going to be a vertical asymptote. So we can draw that one on. We're going to have a vertical asymptote at x equals -2. Okay? So there's our vertical asymptote. Now we just need to figure out where my graph goes, and once we know where my graph goes, we'll put a hole in the right spot. So we need to find my x-intercept and y-intercept. So we're going to take my simplified version. We're going to take this y equals x plus 5 over x plus 2, and we're going to use this to find my x-intercept and my y-intercept. So first off, let's find my x-intercept. So to find my x-intercept, we're going to replace that y with 0. Get rid of our denominator by multiplying by it to both sides. Well, anything times 0 is still just 0. So we're just going to have 0 equals x plus 5 minus 5 to both sides. And we're going to get x equals -5. So we're going to have an x-intercept at -5, 0. For my y-intercept, we're going to plug in 0 for x instead. Well, actually, let me go ahead and put my x-intercept on here. So we're going to have my x-intercept at -5, 0. So -1, 2, 3, 4, 5, 0. Right there. Looking good. My next one, for my y-intercept, we're going to plug in 0 for x. So I'm going to go y equals 0 plus 5 over 0 plus 2. So 0 plus 5 over 0 plus 2. All right, now 0 plus 5 is, of course, 5. 0 plus 2 is, of course, 2. So my y-intercept is going to be 5 over 2. I'm going to go ahead and write that as 0 and 2.5. So we're going to have a y-intercept at 0, 2.5. So 0 up 1, 2, and a half. So now I hope you can see that we're going to be in this section and in this section. Okay? So let's draw my graph on here for that. We're going to hug this asymptote like this. Come down here. Do the same thing over this way. Hug this one here. Come out. Oop, went a little bit too hard on that one. Hug this one here. Come out. Hug this asymptote this way. All right, now, it also says that we have a hole at x equals 3. So what we're going to do is we're going to erase a little piece of my graph at x equals 3, and I'm going to draw a hole right there. So that just shows my graph is going to skip wherever it hits x equals 3. But it doesn't really change my graph. It just affects that one little spot, because that one little spot is undefined. But since it cancels out, it doesn't actually make a asymptote itself. Now for our domain we're going to include both my vertical asymptote and my holes. So my domain is going to be all real numbers except x can't equal -2 or 3. So it's going to be -infinity to -2, union -2 to 3, union 3 to positive infinity. And my range is going to be all real numbers, except y can't equal, well, we look at my horizontal asymptote for that one, right? So my horizontal asymptote was equals 1. So y can't equal 1, so it's going to be -infinity to 1, union 1 to positive infinity.